All right, guys, in the last video, we talked about a polarimeter, and I know you're so excited, and I know that you're jumping for joy, and I know that you can't wait to learn more about a polarimeter and what we can do with it in a lab. I mean, it's so excited. I mean, what a better way to spend your weekend if you're watching this on a Saturday or Sunday than learning about a polarimeter tube. I mean, come on now. We can go have a party on a Friday or a Saturday night downtown and talk about polarimeters all night. I don't think that sounds very fun either, right? But anyway, we were talking about polarimeter in the last video, and a polarimeter, we said, measures something, and a polarimeter will end up measuring a turn or rotation of light. And this is all due to a compound, and we said compounds that are chiral can have 4 different groups attached to them, and because they're chiral carbons and because they are asymmetric carbons, then they will rotate light, and they can rotate light left-handed or they can rotate light right-handed. It's up to us to figure it out, but really it's up to a polarimeter to figure it out because we have no clue what it's going to do by the time that we make a solution, and before we put it into a polarimeter, we cannot predict the rotation of light. So nothing to deal with 3D orientation, nothing to do with is the molecule left-handed or is the molecule right-handed, because very often right-handed molecules, like we said before, can rotate light left-handed or it can rotate light right-handed. It can do both. It just really depends on the nature of the compound. So this is something that we can predict, but it's something that we can look up, and it's something that we can use a reference textbook to help us with. Drastically important. This is one of the reasons that we use a polarimeter, because this gives us idea of what we call the purity of the optical versions of the drugs. So whether they are finished products that form as a drug or whether they're the raw ingredients that go into making that drug, because this is 115 and it's quality control and we talk about pharma a lot, well, all of this is wrapped up into optical activity or optical rotation. So this is another measurement that we can make in a lab just to ensure that things are as pure as what they say. So we'll talk a little bit about this in maybe in this video or in the next video, but stereochemistry and left-handed and right-handed forms of especially drugs are going to be very, very important. The rotation can go clockwise and the rotation can go counterclockwise. Back in the day, we used to use R for clockwise because it's dextro-rotatory, and dextro was R for rectus, which was right hand, and then the counterclockwise is to the left hand, so levo-rotatory, and that was abbreviated as an L. These really are kind of given to something else now. Instead, we don't like to use R's and we don't like to use L's for the way that these compounds rotate light. So after that change, we began to use a lowercase d and a lowercase l. The lowercase d was for dextro and the lowercase l was for levo. That's other abbreviations that we don't really use anymore. And the reason is because of those darn biologists. They tell us what to do every single time and we never fight back. So biology really has a different viewpoint of R's and L's and D's and L's. Organic chemistry has also began to utilize the R, capital letter R, for another type of abbreviation. So it just didn't really make sense because it was making too much confusion instead. So what we do now when we talk about optical rotation and optical activity in a polarimeter, the rotation clockwise, if it goes right-handed, is going to most of the time be abbreviated with a positive symbol, and then the rotation counterclockwise is most of the time going to be abbreviated with a negative symbol. So whenever we see in today's organic literature positives or negatives that follow along with a number, then that probably means that these are going to be right-handed turning or left-handed turning as far as what it does to light energy. The polarimeter. Let's talk about a polarimeter. The instrument that makes this whole thing work. We've got to talk a little bit about the basics and what happens up underneath the cover. So, ta-da! Here we go. Here's a polarimeter diagram, and 1, 2, 3, 4, 5, 6, 7, 8. Oh gosh. So let's talk about each one of these pieces and what they're doing on the inside. So that way, when I use a polarimeter in a laboratory, I know exactly what's going on up underneath the cover. So by the time that I put my sample into the compartment and I put it in there and close the door and hit the big green button, then I'll kind of know what's happening there. Makes me a little bit smarter, makes you a little bit better, more attractive as an employee, because you can talk the lingo and tell them everything that's going on up underneath the hood. But more than that, if something happens and it's not working the proper way, what are some of the pieces that could fail? And maybe how could we get some bogus numbers? So first off, I want to talk about spot number 1. And spot number 1 in this diagram is just really a light bulb. The light bulb for some of the older polarimeters was a sodium D lamp. And the reason is because we always called sodium D very clean as far as the light energy goes. So I want you to think of light bulbs, and light bulbs give off maybe a bunch of different wavelengths. And we don't really want all of those choices. We want to eliminate all of these like random variables as much as possible. So out of all of the things that gives us light energy, what they found is that the sodium element was actually given off just 1 or 2 major wavelengths of energy, and it was very clean. And, you know, we'll talk about this at a different time, especially in our spectroscopy course. But sodium provides a wavelength, one wavelength mainly, that we can pick out, and that one wavelength eliminates all of the other multiple choices of wavelengths that come along with regular light bulbs. So this was a very clean light bulb, and it made our job a little bit easier in something like a polarimeter, because we're only looking at one wavelength mainly now. And that's great news for us, because we don't need to add in any types of extra filters, any type of extra digits, any type of extra settings. So very cheap, very clean, and it makes sense. So in most of the polarimeters, especially some of the older polarimeters, you are finding sodium D lamps that are used, that get plugged in, turned on, and that's our light source. Because think about it, we're using a polarimeter, and if we're using a polarimeter, we are looking at optical rotation, and in order to get optical rotation, ta-da, we need a light bulb. I mean, I think that makes sense, right? So there's our light source, and now we're going to be looking at how our molecule will turn that light source, whether it will turn it left or whether it will turn it right. So in spot number 2, this is the diagram's way of saying, oh, hold up. When we turn on a light bulb, whether it's sodium D or not, but even a sodium D lamp will give us light that goes in all directions. That's what spot number 2 is basically telling us. And we can't really have this either in a polarimeter. So what begins to happen is that we have to start somewhat filtering the light. So light that goes in all directions, up, down, left, right, forward, backward. I mean, again, we've got no control of it at this point. It's just what happens. But we can serve a very simple polarizer, is what we call that. And the polarizer is in spot number 3. So the polarizer's job is to take the light that goes up, down, left, right, back, forward, and then it only allows it to escape in one direction. So what's happening here is that the way that this diagram is set up, there are slits in this polarizer, and the slits are oriented in an up and down rotation, or location. So up and down, up and down, up and down, up and down, up and down. So all of the light energy that goes in all directions slams up against the polarimeter, and then only the light that kind of goes up and down as far as the orientation goes will be able to squeeze through. And then here we've got a even cleaner source of light now for the polarimeter in order to do its job. So at spot number 4, this is just another area where they're saying, listen, you now have, in a way, polarized light. And what's happening is that we're taking the light energy that's going in all different directions, and we're streamlining that down into one orientation only. And in this diagram, it is up and down. And the reason that we're doing that is because this orientation of light is getting ready to slam up against our molecule. So in spot number 5, this is where our sample compartment is going to be. So this is the area that I will load the sample up, and I will place my sample down in spot number 5. And what's happening is that my sample, if it is chiral carbons, and if it is an asymmetric, because they mean the same, then that means there's 4 different groups that are attached. And that means that it's going to take this light and it begins to tick, 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 all the way around. So it's either going to go left or it's going to go right, but it's going to rotate. And this is great news because that's what we want it to do. All right, so anyway, the reason that this polarizing lens here in the front is important is because this gives us one direction, and this one direction is up and down, up and down. Oh, so tick, 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 tick. We start to see that rotation that begins to happen. So out the other end, once it goes through the sample, then this is a new orientation of the light that escapes that tunnel that has my sample on the inside. So that new orientation on the back end of the polarimeter, there is a rotating lens, I guess if you want to think of it that way. And that rotating lens is for the user or for the machine because that also turns. But this is where the detector is at. So here in 7 and here in 8, the 8, it says eyeballs. Well, the 8 is going to be the detector. That could be your eyeballs, but that could also be the eyeballs of the detector. So that's perfectly fine as well. But something has to see the light that's escaping on the other side of the tunnel. And here is spot number 8. That's how it's depicted. So spot number 7 is just really another polarizing lens. That's what this is. It is no different than really spot number 3, except it is rotatable. And that's called the optical rotation, which is why I use that word, because that's exactly what's going on. We're going to rotate that lens left, or we're going to rotate the lens right. And we're going to rotate the lens in that direction until these slits, because look, it still slits just like the other one, until those slits are perfectly aligned with the orientation of the light that goes out the other end. So when I align those up the proper way, what's going to happen here is that light will go through the polarizing lens, which is the second lens that's turnable, and we see that light escaping through because the entire polarimeter now, if I look through it, begins to light up. If this polarizing lens at the back end was straight up and straight down, the light cannot escape through. And that's because the orientation of that light is hitting the lens that is not allowing it to escape because it can't get through the slots. It can't get through that filter. So we've got to turn that polarizing lens until the orientation perfectly matches the orientation of the light after it escaped through the sample. So depending on how we turn this, that is what's going to give us our degrees. So we have a number that's here in front, and that turn is a number of degrees because think about it, I'm turning it in a circle. A circle is 360 degrees, right? So we are reporting how far we have to turn that around that circle degree-wise in order for the light to come through. So that's kind of the theory about what's going on inside of a typical standard polarimeter instrument as you begin to use them in the lab. So 2 lenses, one is somewhat stationary, one allows only one direction of light to come through, and that one direction of light begins to turn if it's optical active, and then out the other end it goes at a different angle than what it came in. So it's up to us or the instrument to turn that second lens left or right, and the magnitude of which we turn until we get the light to actually come through on the other side of the polarimeter too. And then we record our number. So on the rotating eyepiece, you're going to see some numbers or a meter, and depending on how far we turn, that's how we write down those values because they show up right there on the instrument. So here's 2 pictures of different types of instruments for a polarimeter or optical rotation. You're going to have one or the other. This is not something that we can do in the wet lab. We need need at least a piece of equipment in order for this to work for us. So I'm going to see them in probably one of two forms, something that looks like the one here on the left and something that looks like the one on the right-hand side. I want to talk about the right-hand side one first. So the right-hand side one, this is more of the manual option that happens in a polarimeter read. So what happens here is that the orientation is kindly flipped, but all the pieces and parts are there. So you're seeing this cord, and this cord is directed up here into this black box. This is where the bulb is going to be, and the lens, the first lens, is going to be right here. So that filtering lens is going to take that sodium D lamp, and it's going to filter it into that one direction that we talked about. And then here, this plop opens, and I'm going to have a really long glass, probably, sample compartment. So I'm going to fill that sample compartment with my sample, and then I place that long tube inside of the polarimeter, and then I just plop the lid back on, and that way it's in complete darkness. I need it completely darkness because I need you to use some common sense. If outside light was escaping inside of this polarimeter, then the whole thing just doesn't make any sense, does it? I mean, come on now. We did a polarizing lens to do one direction, and if we don't close this thing up, then my goodness gracious, what are we doing? We need to go back to maybe elementary school and talk about things. So either way, I'm going to close the lid, make sure it's fully closed. And then this eyepiece is the piece that begins to rotate. So I will take my little squinty eyes and I will look through that little polarimeter lens. It's like a little microscope eyepiece, and then I'll look and I'll see just pitch black, or maybe some pitch black on the edges and some light in the middle, or maybe some light on the edges and pitch black in the middle. It really depends on the type of polarimeter that I have, and I'll show you that, and I'll talk about that in just a minute. Either way, though, I'm going to see a distorted image. There's going to be partially dark and partially light. So what will happen is that I'll take my little fingers and I'll just turn until I keep turning, and then light begins to come through the eyepiece. And I see that with my own eyeballs. So in the picture, that was spot number 8 because it was a picture of an eyeball. So I am the detector of that instrument, and I tell that instrument when to stop. And I take my hands off of the dial because that's when I tell the instrument when to stop. And then what happens is that here, typically on this rotating piece that you turn, you will record the number on the meter and the amount that you turned it in. And again, you write down positive if you turned it clockwise towards your right hand, and you write down negative if you turn it counterclockwise or towards your left hand. So as we turn to the right hand side, positive would be in that direction. As we turn left-handed, negative would be over here on the left-hand side. All right, so that is how we would use a manual polarimeter. Again, very basic, very simple. These things aren't drastically expensive, but we're really using your judgment call. That's what we're doing, because your values might be slightly different than someone else's because you see something different in the eyepiece of the instrument. And we want to do away with that, and we want something a little bit more automated if we can. So if a laboratory has cha-ching, 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 some money, then they can invest into an automated polarimeter, and that's what you're seeing over on the left-hand side. This automated polarimeter is much better, and the reason that I say that is because all the basics are still here. Here you see the sample cell. The sample cell is right here. It's stainless steel in this picture, and then we fill that stainless steel cell with our sample that we want to measure, and then we close that door and we hit a big old button and it says run on the display screen. So what happens is that this instrument will blank. This instrument knows where the 0 mark is at. This instrument will go ahead and turn that lens for you, and this instrument will report, ta-da, some numbers that we can just write down, and that's really all that we need from it. So it makes life much simpler. I don't really rely on someone's eyeballs to make the judgment call of how far to turn before they stop, because the way the light comes through with your eyes might be slightly different than the way the light comes through with someone else's eyes. Other things that happen with the one on the left hand side is that this has a temperature correction, and this is is great because polarimetry reads do change with temperatures. Temperature is something that I always want to pay attention to. And with the particular automated polarimeters, what happens is that you've got two choices, really. One, you have a thermometer probe, and that thermometer probe is stuck down into your solution, and it will report what that temperature of the solution was as you were doing the reading. Or number two, sometimes you've got an option to heat the sample compartment up to a specified temperature, and it will not measure until it heats that sample up to the temperature that you have keyed into the system. So just depending on really the kind of model that you have, the needs that you've got, temperature is going to be a thing that can change these values, maybe drastically if you're not very careful. Over here on the right-hand side with the more manual method, this manual method, you really don't have that option. You have to kind of record the temperature separately on your own. You've got to apply corrections and equations and math, and who wants to do all of that? Nobody. So here, automated systems really come into play much more. Our laboratory in Chemtech side of the house, we have a Rudolph Research polarimeter, and this is kind of what ours looks like. Again, different models, different years, different shapes. They do updates to them, but all in all, this is kind of what ours is. Once more, there is a sample compartment. That sample compartment is opened up, and here I have a sample cell that I will place inside of the machine that will hold my sample that I want to measure. I then close the door, and then just like before, there's some readouts that will show up on the screen, but I'll hit a big button, and that button will say read, and then that's really all that I have to do anymore for polarimetry. So again, once makes my job much easier than what it was before. Here is a picture of inside of the polarimeter, maybe a little bit closer. The position of the sample compartments in these polarimeters, it doesn't really matter. You can put them in the middle if that's where you like, and that's typically where I do them. Or you can push them over to the right-hand side, or you can push them over to the left-hand side. Doesn't really matter. The only thing that I would say is just be consistent with it as you begin to run samples in a polarimeter. You don't want to be changing the location of that polarimeter cell over and over and over and over and over. It should not make a difference, but just in case, I always like to play it safe. And I also think that putting it in the middle gives me a little bit more wiggle room and freedom on either side for things like these little temperature probes that need to go into the solutions and so forth. And that's really what you're seeing here on top, this kind of black knobby thing that has this stainless steel probe that goes inside the solution. This has a cord that gets connected to the left-hand side, and that is a temperature or a thermometer probe. So that way on the report or on the display screen, it's telling you what this temperature actually is of the sample when it made its measurement. Over on the right-hand side, you're seeing different versions of sample compartments. Here we have a stainless steel one, and the stainless steel has what we call the cup on top. The cups are very easy. You just pour your solutions into the cups, and you just slowly fill it up to the top, or not to the top of the cup, but at least to the top and a little bit above the sample compartment. So that's why the cup is there. It makes filling these sample compartments way easier than some of the other old school polarimeter tubes that we used to work with. You're also seeing that inside of the polarimeter here in the picture as well. This polarimeter sample compartment has this yellow solution on the inside, and you're seeing that they have overfilled it, and they didn't go to the tip-toppity of the cup, but they went about halfway. So at least you're halfway, and what you're looking for are bubbles. Bubbles are bad. Bubbles take up space. Bubbles prevent kind of the rotation of the light and maybe even the light coming through. So you want to double check these, and you want to make sure that no bubbles are present when you begin to fill the samples in the compartment cells. But the cup models, we really don't worry about that too much. They are often the easiest for people to use and the simplest and quickest in order to fill and to dump. Some of the other options, and by the way, you know, glass can break. break, and we hate if you break our polarimeter cells. And then stainless steel is a little bit better because it's going to withhold a little bit of abuse. So you don't really have to worry about dropping it and cracking it so much, but with the glass cells, you do. The problem with the stainless steel, though, is that you can't see through them. So for instance, here with the glass one, I can see through it, and there are no bubbles in that chamber. Like, I don't even have to check it. I can look at them and I can just know. But in the stainless steel one, I can't really do that. So in the stainless steel tubes, we still have to check them, though, for bubbles. And what happens, you're going to take your little squinty little eyeball, and you're going to look here at the end of the polarimeter tube, and you're going to look through it. And if you can, see out the other end, and you can clearly see out the other end, then that means that you probably do not have any air bubbles, and the sample can be placed inside the machine and we can run it. But if you look through those sample compartments and it's just black and you can't see through them at all, there's no image, it's just looking like you're looking into a really dark closet with all the doors and the lights shut, then it's not really loaded the proper way. You probably have a bubble or something preventing the light coming through. So if you cannot see through it, the instrument cannot see through it, and if the instrument and you cannot see through it, you can't make measurements. All right, that's as simple as how it is. Okay. Next up, these sample compartments do come in smaller or longer versions, and that's what you're seeing here. These also, though, do not have a cup model. These have like syringe adapters on them. And these are the syringes that we just use for multiple purposes in the lab. I mean, there's nothing special about these syringes. There are a dime a dozen. So I just pull sample up into that syringe and then plop onto the syringe kind of adapter. It goes right there. And then the only thing that I have to do is squirt sample slowly into the sample compartment. The problem here, though, is that air bubbles are notoriously a problem here. And then you're going to insert sample until you start to see a little drip, 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 drip out the other side. And you're going to wipe that off because you don't want contamination there. But you want to wipe all of that dripping off because that can be a problem if you leave it behind and everything gets sticky and everything starts to kind of become a mess. And then we're going to start screaming and yelling and complaining with you. And then you also see kind of a longer tube made the same way. You see those syringe adapters on the side. You do the same thing here. Take that syringe and then squirt sample into that polarimeter tube until it goes drip, 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 drip out the other end. And then you just wipe that off. And then again, you want to take your squinty little eyeballs and then you want to look through the polarimeter tube and make sure that you can see all the way through from beginning to end. And then if you can, it's ready to be loaded up. As far as the manual option goes, though, these were the old-timey polarimeter tubes, and these were always difficult to get loaded up the proper way. What would happen with these old-timey, more manual ones is that these pieces would be screwed off, and then you would fill the tube up to the top with your sample, and you would kind of want to overfill it in a way. You would want that little bubble on top, and then you would slide a little piece of glass over that extra to push out any of the air that might stay behind, and then you would screw this end piece back on, and then you would take the tube and you would kind of flop it up and down, and you would not want to see any type of air bubble on the inside. If you had an air bubble, you had to add more, do it all over again. I mean, it was a mess. But these were the traditional cells back in the day. They were a problem because of that reason, and the automated instruments just make this a little bit better for you, and we're very happy because of that. As far as the manual instrument goes, remember that's something that looks like this over here on the right hand side. When you look through that eyepiece, what do you see if you had to use a manual one? Well, you would see one of two options here. Most of the time, people would see the light edges and a completely dark center. And what this is doing is it's letting you know that, yes, your instrument is on. Yes, the light bulb actually works. And the reason I know that is because light is coming through the outside edges here, and I see that. So that means that my instrument is at least on, my bulb is working, and light is coming through. So it's just really a confirmation thing. And then in the center is typically where this dark area would be located. So if you have a chiral carbon with 4 different groups that are attached that can also be called an asymmetric center, then it's going to rotate light and you will see that dark band appear. So I would take this eyepiece and I would take my little squirrely little fingers and then I would turn it left or turn it right, and then I would keep turning, and this dark area will begin to lighten up. And then what happens is that you would get to a point where it all perfectly matches. So the dark area goes away, but more importantly, the intensity of the light is the same in the entire eyepiece. That is really what we're after. And that's what a lot of people were confused about, because they might have gotten to a point where all light was coming through, but they were at a point where the intensity of the light was not the same. So you could still see a division line, and you don't want to see a division line in these polarimeters when you begin to use them. So we're looking for something universal. We're looking for something, I guess you could call it homogeneous from top to bottom. It looks the same from left to right, from top to bottom. There were some instruments also that would kind of peg dark sides here with a light side in the middle. Again, the same thing happens here. Sometimes this would be due to like an overturning of the dial, or sometimes it would just be the way the instrument's manufactured. It just really depended, but still the same concept is in place. You look through the eyepiece and you begin to turn. And as you begin to turn, you turn, until you get to something that looks very universal from top to bottom, left to right, and the light intensity is the same no matter where you look. So that is a little bit about the manual methods that happen in a polarimeter. And we do have a few of these, but we use them as backups. We use our automated instrument a little bit more, and I think that you'll be very pleased with that, because if we brought out some of our old school ones, I mean, they look like they should be in a museum at this point by the way that they look. All right, so that's where I'm going to stop this video. In the next one, we're going to talk a little bit more about a polarimeter. We're going to talk more about chirality and stereochemistry and why it's so important. And then we go in and maybe we'll hit a few calculations as well. So once I get raw data from these instruments, what should I be doing with that raw data? And that requires an equation with a little bit of math and a little bit of calculator work. So here we go. We're still talking about optical rotation, and we're not finished yet. So come back and see me. I'll be waiting patiently whenever you come back from the bathroom from your pee-pee break.